Hello students, welcome to EPG Pathshala. I am Dr. Amarjit Singh from Himachal Pradesh University, Shimla. Today we are going to discuss about a module called Surfaces, Interfaces and Voids from the paper Solid State Physics. So students, let's see what we are going to learn in this module. What are our objectives? So we have already seen this point defects or defined point defects in earlier module. In this module, let us talk about line defects. Let us talk about 2D defects, uh, just like surfaces and interfaces interfaces between two crystals, grain boundaries and tilting of the grain boundaries, interfaces within crystals, and also 3D defects just like volume defects, and most importantly how to characterize these defects using electron microscopy. So we will tell little about these two techniques. So electron microscopy uh, will be used for a small length scale objects, and when I say characterization, it means we want to find out the size, the shape, all these things about the defects. Now let us say what do you mean by a line defects? These line defects are so called uh, um, dislocations. You have seen that if you pull a material, if the material has a strength, it is elastic, it comes back to its original shape. But when you push it or pull it beyond its limit, or it causes a plastic deformation. Plastic deformation is when it does not return to its original place. So usually there is a slip of the planes in this kind of deformation inside the crystal, and a permanent deformation kind of takes place. There can be a void, or you can say the atomic bonding between some planes are disrupted completely, and we have created some linear defects, some planar defects in this kind of when performing this kind of deformation to a large extent. So as we learned that defects can be of different type, we have already learned this point defects, and in point defects uh, we found that at some particular point either there is an extra atom or there is a missing from there. So this defect can be uh, uh, of different type and of different geometries. So with respect to the dimensions, these defects are defined. So there is another class of defects which is called line defects. So why line defects? Because along a line, if you in a crystal, if you go and along a line you find some defect, so that the defect is existing along a particular line for a sufficient distance, so then it is basically a line defect. So in technical language these are called dislocations, and these dislocations are one dimensional defects around which atoms are misaligned. So in this dislocations also we have two different kind of dislocations. One is called edge dislocation and another is called screw dislocation, and of course these we will discuss in detail and in the next slides. So there is also one term called Berger's vector which will come into the discussion in this. So with respect to this Berger's vector, we will understand that how we are going to classify the edge dislocation and screw dislocation, and sometimes they can be mixed also. It means in a given specimen you can have edge dislocation as well as screw dislocation at the same time. So in this slide we have shown here edge dislocation. So you can see that on the right hand side we have a figure, and on top of this figure this is this atoms or the planes are nicely arranged, but as we come below and after this third layer, there is an inverted T, and below that you can see that a particular line of atom is missing just below that, and due to this there is a distortion around this inverted T. And now you can see that below this T there should have been an entire line, so that this crystal would have been complete, and there should not have been any plane missing from there. So you can see the entire row is missing. So along this line there is a defect, so that is why we call is line defect. And this kind of missing of a plane along a line is what is defined as edge dislocation. So in this slide we show you another type of line defect, that is screw dislocation. So the geometry of this dislocation is clearly visible in this diagram, but let me draw an analogy that if you have an eraser which you use for erasing when you write with pencils, so you cut it somewhere from the middle and do not cut it through completely, but stop somewhere in between, and now you apply a twist at the upper portion, and you take it on the other side and lower portion on opposite side, and you will see that you will create a kind of shape which is visible in this figure A here. So it is as if near the point from where this cut ends, you rotate the entire structure above and below. So that is why it is called as screw dislocation. So this dislocation is created due to some line perpendicular to that line. You have an axis of the rotation in this figure. Now this will be more clear in terms of Berger's vector, which I am going to talk in next slide. Now in this slide you can see that there are mixed type of dislocations. There is a blue arrow which shows screw dislocation, and there is a edge dislocation. They both can be present at a time. So this is a mixed dislocations, and when you take the intersection from the point of this dislocation, so that is shown on the right side. That's how this dislocation, you can see that it is visible, it has a particular path at which our crystallinity or order is somewhat lost. So this is another type of defect. 2D defects, interfaces. So till now we have discussed point defects and line defects. Now this is a defect in a plane. So this is two-dimensional effect. So the solid surface itself is a defect, as we can see that surface atoms experience asymmetric environment on two different sides of the interface. Impurity atoms can also be adsorbed at the surface, which is usually rough. So the idea is that when you see some atom which is buried deep inside a crystal, now it has a symmetric environment. I mean, on all sides you can see that it is bonded with atoms and it is not exposed to environment. But when you come to the surface of a substance, you can see that environment is not symmetric for the atoms which are sitting on the top. On one side they are bonded with solids, on the other side they are exposed to environment. So when they are exposed to environment, some atoms, gas molecules can interact with the top atoms. They can chemically bind there, they can physically bind there, or can also diffuse to certain extent inside the solids. So this kind of defects you usually see that they exist in a plane. So there is a plane in which this layer of or concentration of defects will be there near a plane. So that is what is called two-dimensional defects, and that study of two-dimensional defects is a subject of surface physics. So one can study this under the area of surface physics. So we are talking about 2D defects. So there is a um, also this one kind of defect due to the unbalanced electrical nature of the planes. The interfacial tension of a surface in ionic solid is strongly affected by the distribution of electric charge. As you can see in this figure, this is a figure of sodium chloride showing an electrical neutrality in certain planes, and in another plane it is not electrically neutral. So 100 plane is electrically neutral and 11 plane is not electrically neutral. As you can see that on 100 plane you have equal number of positive and negative charges. So you can see this, the surface of 100 plane, apparently it looks to you that there are 5 white balls and 4 dark balls. So how does it define neutrality? You need to understand that from all these 4 corners 1/8 portion is contributing. So this half atom is contributed from all 4 corners and half atom is contributed from the face. So this constitute a 1 atom. Similarly, the 4 dark atom at the edges, they also contribute 1/4 each. So there is an equal amount of positive and negative charges. So it's electrically neutral. It does not influence another layer which is of the same family, and because this will have also electrical neutrality. But if you see 111 plane, there is an axis of a positive charge over there, or in another plane there will be axis of negative charge. So that creates a kind of electrostatic interactions between these planes, and so that is you can say that cause a defect in the plane. It could lead to local distortion in the system. In strong ionic materials, the electrically neutral surfaces 100 have much lower interfacial tension than the charged surface such as 111 in above example. The relative interfacial tension of charged and uncharged surface can of course be altered by the addition of surfactants, which are often preferentially attracted to the charged surface. I mean, here we can play little bit with the chemical synthesis and some sort of uh, work with the surfactant materials which are itself charged, and when we apply these materials to such kind of surfaces, we can neutralize it. So basically we can fabricate or synthesize some different kind of charge environment given this kind of charged planes. Interfaces between crystals. The preferred shape of a crystal is bound by free surfaces is the one that minimizes its total interfacial energy. The macroscopic surface of the crystal can always be treated as if it were made up of facets, the kth one of which has an area AK and interfacial energy sigma k. The energy is then E is equal to sum over k sigma k AK, which is written in the formula. So you can see the diagram on the slide on top, which is an entire solid, and it is basically a collection of pieces. You can see that because this is a three-dimensional system, and on just because we are drawing it on a slide, we cannot see all 3 dimensions, but you can see that each of the the portion of this is attached to nearby portion, and there is a boundary in between the grain. So these are crystalline grains, and this is usually the samples or crystalline substance we get in laboratory where their nature is polycrystalline. Entire system is hardly single crystal, or if it is not made so with some special purpose, usually you get polycrystalline materials. So you can understand that when you cross a boundary between one grain to another grain, there is a symmetry breaking in terms of translation, and in between the boundary some of the area is disordered, and that disorderness uh, goes along a plane. So this is another kind of plane defects between the grain, because they have facets and one facet is attached to another facet. So this is called interfacial defects, and those exists in polycrystalline samples. Grain boundaries and tilt. A tilt is a vertical array of parallel edge dislocations. When a tilt boundary is introduced into a single crystal, it creates misorientation by a tilt angle theta between the volumes of crystal on either side. If the dislocations in the boundary have Burgers vector b and are separated by a vertical distance d, then the tilt angle theta is given by the formula theta is equal to tan inverse b upon d. So as you can see, the same on the left hand side in the figure, that there are two kinds of grains with the parallel lines. These are the crystalline planes and they are tilted with each other, and there is an inverted kind of T. So these are dislocation lines perpendicular to the plane, and the separation between these T is D in the formula. So idea is that we can uh, determine this tilt between the plane boundaries using diffraction method. We can also um, use direct microscopic methods and electron microscopy, and we can then calculate Burgers vector using this given formula, or if we know the Burgers vector, we can calculate theta. So on the left hand side bottom, you see a figure. There is a dotted line in between two phase. So this dotted line shows that there is a plane, and this plane is perpendicular to this board and screen. So this is one kind of plane dislocation we know. Interfaces within crystals or stacking faults. You can see there is another type of defects which can occur in crystal. The simplest example of stacking faults are found in closed pack structures using the notation introduced in the previous chapter. A stacking of close packed plane in the order ABC ABC generates the FCC structure. A stacking fault occurs whenever this pattern is broken. For example, in a crystal with the local stacking sequence ABC, BA, BC, the extra B plane in the middle constitutes a stacking fault. This can be extra B plane, or there can be a missing plane, and as you can see that in the diagram, it is shown in three different colors, A, B, C, and then A, B, and you can see that the C type, there is some extra point, some extra line has been introduced on left hand side. So this has created a kind of stacking fault with respect to on the other side. So you can see that we have here dots which are repeating one after the another, and on the other side that repetition is missing because of this stacking fault. 3D or volume defects. So let us also mention this 3D and volume defects. So these are pores, cracks, and foreign inclusions. So pore can greatly affect optical, thermal, mechanical properties. So pore is basically, it's not missing of one or two atoms. It's a, let's say some large number of atoms are missing from some place. So that creates a void. So it's a three-dimensional defect. It is different from point defect. In point defect, maybe one or two atoms are missing. And then cracks, and as you can see in the diagram, so that is a three-dimensional defect because it goes along all three dimensions. And foreign inclusions means some extra material in the pore or cracks is filled from somewhere at a length scale quite large. So that also is a sort of three-dimensional defects in the system, and this affects the property of the material, and at large length scale, this occurs at the large length scale, so it will have its own consequences. So students, let us summarize what we have learned in this module. So we have learned line defects. There are two kinds of line defects. One is edge dislocation and another is screw dislocation, and we can identify them with respect to the Burgers vector. And another type of defects are surfaces and interfaces of crystalline material act as a 2D defects. So surface itself is a defect, interface itself is a defect, uh, and foreign atoms adsorb at the surfaces leads to additional defects. If you have a surface and you have some chemical adsorption or physical adsorption of these atoms on the surface, so that is another kind of defect. Since the materials are usually polycrystalline, the boundary between the crystals are called grain boundaries, and we can understand that these grain boundaries have amorphous character because the order is lost in this particular region. So when we cross from one boundary to another boundary, we've passed through a region of disorder, or we can say a surface, because one grain is attached to another grain through a facet, so it is a two-dimensional defect. Grain boundaries are two-dimensional defects. And then we also learned about stacking faults, that when you are having a certain type of plane, let us say A, and you have another type of plane, let us say B, and then you have C. So there is a stacking of A, B, C like this. If it goes like that, sometimes this stacking, there can be problem in the stacking. Some of the order is missing, let us say complete C is missing, or complete B is missing, or there is an extra layer of C or B, anything. So when you are constructing a crystal by stacking this A, B, C like this, so there is a possibility of occurring of stacking faults. Now when it comes to point defects and line defects, they are so small that these cannot be observed by optical microscopy unless the size of the defect is of the order of some microns. So we need to take the help of electron microscopy, because with the electron microscopy we can go to the resolution as down as 1 angstrom or even smaller, and we can really map the atoms, we can really see the atoms, how they are arranged, and in a pattern, or if this pattern is disturbed, that would become visible in SEM and TEM techniques that we have discussed. Thank you.